and welcome to the MOOC on optical communications. In this module, we will first look at eye diagrams, which is one of the visual ways of talking about the performance of an optical communication link, and then talk about higher order modulation or spectrally efficient modulation techniques, which are going to increase the spectral efficiency of the current optical communication systems. Before that, let us look at the eye diagram as I said. Okay. So, we have already seen how to characterize the performance of an optical link. Suppose you have an optical transmitter, okay, which is sending out a sequence of bits. So, let us call this as 10 10 and so on. Okay. This I am assuming that we are looking at the digital optical links. For an analog optical link, the performance measure that we are going to describe, what is called as eye diagram, does not really apply. For an analog communication link, the performance is usually quantified by the signal to noise ratio, and if you have transmitted a certain waveform, the fidelity of the system, that is how good the system is described by how less noisy and how you are able to reproduce the waveform at the receiver. So, this eye diagram is something that is used only for digital communication systems or mostly for digital communication systems, and we are going to look at what this eye diagram is. So, you are going to transmit this optical signals which are modulated 10 10 by by whatever the bit pattern that you have. Now, when the signals go through a fiber, right, we already know that fiber introduces loss, which means that the amplitude of the signal starts to reduce, as well as introduces chromatic dispersion. The fiber chromatic dispersion causes the optical pulses to spread out, causing an intersymbol interference. So, at the transmitter you might actually have a nice symbol, okay, this is corresponding to 1, this is 0, and then you have a 1 again, and then you have a 0 and so on. Okay. So, these symbols are very nice in time, okay, which are very clean, no noise, no going outside the allotted bit interval or a bit slot. So, these are probably for example, the bit boundaries that one can assume. This bit boundary is slightly gone on the other side, but it is okay, you can kind of understand what I am trying to convey over here. However, once you get this waveform at the receiver side after you have photo detected, you would have noise in addition to loss as well as chromatic dispersion. Loss you have somehow overcome by putting an optical amplifier. Chromatic dispersion can be compensated, but if it is not compensated, then it will also show up in the final result. Noise of course would always be present no matter what you do. Noise cannot be completely eliminated from the received waveform, and you are as you know, how do we interpret the digital signals. So, at the receiver side what we do is we actually sample this signal, right. So, we actually sample the signal value and subject this sample value in order to a, so we sample this one generating the signal samples, let us call this as RK, and then subject these received samples RK to some kind of a threshold detection, right. So, if you assume that you are working with a simple on off keying system in which a bit 1 is represented by a presence of a pulse and 0 represented by no pulse, then if the value of the sampled signal, which of course will be the original signal plus there will be some noise, if it is greater than a certain threshold, then you declare the bit as 1, if it is less than the threshold, then you declare a bit as 0. Okay. In the case of a tie, of course, it is possible that you simply allocate the detection to either 1 or 0, does not really matter. And how frequently you are going to make errors, right. So, when you have actually transmitted a bit 1, but you interpret the result as a 0, we had actually calculated what is the probability of this happening, correct. We had also calculated the probability of mistaking a 0 into a 1, these were known as the conditional probabilities, and combined with the probability of transmitting a 0 and a 1, we obtained expression for what is called as probability of error. So, this probability of error multiplied by the bit rate is what we called as the bit error rate. In order to talk about bit error rate, we also introduced another parameter called as Q parameter or the quality factor. Okay. So, we talk of Q as a Q factor, which basically measures some sort of a margin between the photocurrent, that is the difference between the photocurrent when the bit 1 is transmitted and photocurrent when bit 0 is transmitted, to the noise that exists in the system. Okay. So, sigma 0 and sigma 1 are the RMS values of the noise current when you have transmitted bit 0 and bit 1 respectively. So, we have looked at BER as a performance measure, we have looked at Q factor as a performance measure, but these measurements do not tell you anything, they do not give you a graphical view of what is happening to the system. Moreover, they are also not going to tell you what is the permissible sampling error time that I have. Okay. So, if the chromatic dispersion is pretty large, then the received pulses will start to behave very strangely. So, let us say these are my original bit boundaries and I have a pulse, okay. This is 1, this is 0. So, this is bit 1, this is bit 0 and then I have one more pulse, okay. So, this corresponds to bit 1. When the chromatic dispersion is very large, then what happens is that the signal would almost be flat, okay. So, the signal would almost be flat in the sense that it would be spread out quite a bit, and then in the slot of 0 you might actually see something like this, okay. So, this would be the situation when the chromatic dispersion is very large. However, this does not enter into the BER or the Q factor, not at least until you make some additional modifications to the expressions for BER or the Q factor. So, to analyze the effects of chromatic dispersion on the pulse, okay, what is the rise time of the pulse with 1 and 0 or transition from 1 to 0 and 0 to 1 transitions when you have chromatic dispersion, also when you have noise, and whether all these symbols are coming in at their corresponding bit boundaries. For example, in one time you have this particular bit boundary, signals are arriving within that, next time there might be a small delay, okay. So, you might not have a large amount of chromatic dispersion, but then you have a small delay, okay. That should have been just a small delay out there, and you might also have situation where this delay can be either earlier or later, okay. This will be a very important factor because earlier you were sampling at the maximum point, okay. Now, because of this error or the jitter in the arrival, so your sampled voltage what you have will actually be less. For example, let us say this is the point where we were sampling originally. So, this is my original sampling point. Now, because of the delay or the jitter which is random, the signal did not arrive at this point, but rather the signal peak occurs after some time. But my sampling time is still the same, right, and what would be the sampling value? That would be this blue color one. If you look at the difference, right, there is actually a difference between the blue dot and the black dot, and this difference means that the amount of current that I would have had when there was no sampling error has now been reduced. It is not that the current has decreased in amplitude, the current peak simply occurs at a later time. You can very well see that if the peak occurs at an earlier time also, you will lose a little bit of a current value out there, right. So, the Q factor will slightly reduced. All this information is captured by what is called as the I pattern of the system. In the I pattern of the system or of the link, what we do is we send in sequence of waveforms, okay. So, we send in a sequence of bits and we look for 4 transitions, because this is an on off keying, we look for 4 transitions. One is 0 to 1 and you have 0 to 0 transition, you have 1 to 0 transition and 1 to 1 transitions, okay. These transitions which are at the lower side, which is 0 to 0 and 1 to 1, do not really tell you much except that they tell you how much noise exists, okay. And the transition from 0 to 1 usually gives you the rise time of the system, and the transition from 1 to 0 will give you the fall time of the system. Usually these two are equal to each other, but they may not be equal in an actual scenario, okay. So, an I diagram actually captures that. What we do is we look for 0 to 0 transition, which like from 1, we take one bit boundary at the middle. So, this one is one symbol and this one is the next symbol. We take these two symbols and start overlapping the signals, okay. So, we start overlapping the signals like this, okay. You can see that the 0 value is not exactly 0, right. There is actually a small width within which you are able to get any signal. So, even though you have transmitted a bit 0 and the next bit is also 0, there is a certain amount of change in the amount of the current I0 value that you are going to get even when you are transmitting only 0 and 0, and this of course will be the RMS value of the noise that would be added when you have transmitted a bit 0. Now, consider what happens when you have a 0 to 1 transition, okay. So, let us say this is the 0 to 1 transition and this is actually already not a very good transition that we have, Okay. So, you have this 0 to 1 transitions. If you have the present waveform as 0 or the present symbol as 0, the next symbol as 1, those transitions are again matched in this way. You will also have a 1 to 1 transition, which is usually much more noisy than the 0 to 0 transition. Of course, the reason is very well known to you. The reason is because sigma 1 is larger than sigma 0. So, because of sigma 1 being larger than sigma 0, this would be the transition that you are going to get. Also, you will have a 1 to 0 transition. Okay. So, this would be the 1 to 0 transition that we have. Okay. So, hopefully this is all symmetric, or at least it should be looking symmetric to you. Okay. So, this particular diagram that we have is what is called as the eye diagram. Okay. But normally you do not put the eye diagram in this way, you just kind of shift it slightly. Okay. So, in the sense you look at two transitions, so that you get a nice way out like this. Okay. So, this is 0 to 0 transition, this is 1 to 1 transition, and these sloping lines are 0 to 1 and 1 to 0 transitions. Okay. Again, the diagram is slightly off, but look at the textbook that we were that we are looking at in the course, and as I said, this will tell you the noise limit for 0, this will tell you the noise limit for 1, and what you see here, this should have been more symmetric. So, let me try and make it more symmetric over here. So, this should have been the symmetric point. Okay. So, if you look at this way, this is called as the eye opening. Okay. Eye opening tells you how much noise margin that exists in this particular link. Okay. If the eye opening is small, then it means that the system is very noisy. Okay. If the eye opening is large, then the effect of noise is very small. Also, the slope of these lines that you have will tell you the transition from 0 to 1, or will give you the rise time. The slopes of these lines which are going from 1 to 0 will give you the fall time. Rise time and fall time are usually the same. If there are any other imperfections, for example, if there is a transition from 0 to 1, but because of a low pass nature, sometimes, or there is a certain capacitive element in the amplifier, you might actually see an overshoot. Okay. And you might also see an undershoot. So, all these effects are captured by the eye diagram. Okay. The best time to sample is right in the middle when the eye is maximum. Okay. So, this is the best time to sample. Why? Because you get the largest margin over here. If you decide to sample somewhere over here, the amount of margin that you are going to get with signal to noise is much smaller than the corresponding noise margin that you are going to get. Okay. In a particularly bad scenario, you might actually have a situation where the noise is such that the eye is barely opened. Okay. So, you might actually see that this is the eye opening, and this eye opening is almost equal to 0, indicating that the system is highly noisy. Okay. If this slope, by measuring the rise time of this one, of this slope from the transition from 0 to 1, it is possible to link both rise time as well as fall time. If you measure, it is possible to find out how much the chromatic dispersion that existed. So, if you know what is the rise time of the pulse before propagating through the fiber, then you can look at what would be the situation after it has propagated through the fiber, and from there estimate what is the chromatic dispersion. Okay. It is also possible to estimate the BER as well as the Q factor. Of course, Q factor is simply this margin that you are going to get. From the Q factor, you can go back and measure BER. So, the additional advantage of having eye diagram information is that it is possible to extract the non-visual performance metrics, that is Q factor and BER, both from the eye diagram. So, let us stop our discussion of the eye diagram over here, okay, and then look at this next topic, which hopefully promises a lot more fun than what has been so far. Okay. One of the things that we talked about, right, when we went from the RF systems or the wireless systems or the copper cables, from those systems we went to the optical communication systems starting in 1970s, and today virtually all of the communication except for some satellite communication, okay, and underwater very specialized communications happens more or less by optical means. Even the wireless base stations are linked by fiber optic cables, fiber optic networks, so that only the mobile part, that is your handset to the base station communication and handset to handset communication, happens over a wireless channel or such as an atmosphere or an air. But even with the almost infinite bandwidth, or the enormous bandwidth that the optical fiber offers currently, right, the demand for traffic, as more and more people get interconnected to essentially internet and start using these highly demanding applications such as video on demand, or downloading movies, uploading large data files. Okay. So, when these activities happen, even the supposedly large capacity optical network comes under a lot of stress. Okay. And this has been particularly experienced over the last decade, that the demand for bandwidth is going up and up unless we actually take care of upgrading the mechanisms of optical communication systems, then it would not be possible for us to meet the increasing demands. Of course, people are always looking forward in the future, and about 15 years ago developments actually started towards the next generation. So, remember in the first few generations your data rates were very small, then came the 2.5 Gbps standard. With the help of optical amplifier and WDM revolution, we pushed the data rate from 2.5 to 10 Gbps, and there was an intermediate 40 Gbps upgrade. Now, the current technology is actually at 100 Gbps. Okay. So, we are now able to send over one wavelength, or at least in a very small band as we would call, we are able to send about 100 Gbps of data, and over a DWDM system which consists of about 200 channels, at the same time you are able to send more than terabits per second data. Okay. So, this large data rate one would think should be sufficient, but unfortunately it is not, is going to be further increased. Okay. However, what technologies have actually gone from for us to go from a simple on off keying 10 Gbps, I am of course saying simple only in the relative context. Okay. Even the 10 Gbps systems was not very simple, lot of system improvements had to be put in to get to 2.5 to 10 Gbps. But from 10 Gbps to 100 Gbps has been a real challenge, and people have met this challenge by coming up with what is called as spectrally efficient modulation techniques. Okay. This seems to be a very fancy word, but the simplicity of this scheme is that in the on off keying systems you actually used only the intensity of the signals. If the pulse was present you had a bit 1, if the pulse was absent you had a bit 0. However, we never modulated the phase of the optical carrier, and to go from 10 to 100 Gbps people did exactly that. So, they went from simple on off keying modulation to a complicated, slightly complicated in terms of the modulation technology, into what is called as QPSK transmission. We have already looked at QPSK in the earlier modules, we will simply very quickly review all those things. Okay. And not satisfied with QPSK, people went further up. Okay. You now have 8 array PSK, in which 8 phase states are created at a particular intensity level. Then came the 16 QAM, which could be constructed in many ways. You have the star QAM and you have the square QAM. Okay. From there people went on to 64 QAM, and that seems to be the ceiling currently with coherent optical systems. Now, only at the transmitter side was not the revolution that happened. I mean, after all, you could always do the phase modulation even 20 years ago, but the real revolution lied in the receiver side, because in modulating the phase you are encoding information in the phase of an optical carrier, and there exists no method to directly tell you what the phase of a sinusoidal signal is. You can actually try and do that one, right. There exists no detection mechanism. Okay. Especially the photo detectors cannot detect phase, they are immune to phase. What do they detect? They only detect the modulus square of the incoming optical signal. So, all the phase information is washed out. However, using a coherent detector, which means constructing a local oscillator, you are able to extract the phase. So, you are able to convert the phase fluctuations into intensity fluctuations, and by looking at those intensity fluctuations you are able to infer what bits or what symbols were transmitted. However, this also means that the local oscillator and the original signal that is being on the frequency, they have to be synchronized with each other, right. If this has a certain phase noise variance, or the phase noise variation, then the local oscillator also has to track those phase variations. So, they have to be in phase with each other for coherent systems to work. In the 90s, when this concept was widely known but was not really applied, the main bottleneck there was the optical phase lock loop. You could not really build optical phase lock loops with when the transmitter and receiver were widely separated, and such that the constraints on an optical phase lock loop was much more than constraints on an RF phase lock loop. Okay. So, because of and the primary culprit of all that was the laser phase noise. So, today we have brought down the laser phase noise with the line widths ranging from few hertz to about 100 kilohertz in commercial systems. Even with that lower phase noise, it is still very difficult to implement a distributed optical phase lock loop. Okay. Rather than that, what people do is they let the local oscillator work on the coherently receiving the signals. Whatever the phase imperfections that exist would now be mitigated using digital signal processing. While you are using digital signal processing to mitigate the phase, you can also mitigate the frequency offset. That is, your received local oscillator frequency, if it is completely different from the transmit signal frequency, right, and if this offset does not remain constant but rather keeps changing, then you will lose performance. Okay, the performance will suffer. Even if the offset is constant, then the performance still suffers by about 3 dB, as we will see in one of the exercises. So, to obtain the best performance, you have to keep the frequency offset equal to 0. Again, this topic can also be done by, or this task can also be accomplished by digital signal processing. Finally, you can also compensate for the chromatic dispersion that exists in the fiber, not by going to the fiber based mechanisms, but rather using DSP to perform all these tasks. Okay. With considerable use of DSP algorithms, it is now possible to transmit data at 100 Gbps, and in the next module as we begin, we are going to look at in this module as we begin later, we are going to look at some of those advanced modulation technologies, okay, and we will talk about what is the drawback of these systems later on. Okay. How can we first improve the spectral efficiency? We define spectral efficiency as the efficient utilization of the bandwidth in terms of how many bits per second, or what is the bit rate to the bandwidth that we have utilized. Okay. So, with that, let us jump in to look at some of the approaches people have taken in order to increase the spectral efficiency. Okay. So, spectral efficiency is given by the bit rate to the bandwidth that you have used. Okay. For a simple on off keying, this spectral efficiency is actually equal to 1, because the bit rate is so and so bits per second, and it requires exactly the equal amount of bandwidth that you have looked at. There seems to be, to increase the spectral efficiency, there are two major approaches. One is to use what is called as single carrier systems, but use higher order modulation. Okay. So, with higher order modulation, your basic modulation formats start with say a 4 PSK, a QPSK, or 8 ARRI PSK, or 8 PSK for short. You have 16 QAM and 64 QAM. Okay. All these higher modulation technologies, what they do is they try to assign more than 1 bit per symbol. Recall your on off keying system. In the on off keying system, if you transmit 1 bit, okay, so if the bit is 1, the symbol that was transmitted was also 1, because the bit 1 mapped to 1 here. If it was bit 0, then the symbol was also 0. So, in this case, each bit was mapping only one particular symbol. Okay. With 4 PSK, which we have described in one of the earlier modules, you have options of 4 states. Okay. 4 phase values, this is the I and the Q axis of the system that we have looked at. So, these points are called as the constellation points, and the entire thing is called as the constellation, right. We have looked at all this in one of the earlier modules. With these 4 phase states for the 4 PSK, it is possible to associate 2 bits per symbol. If you prefer a gray coded version in which the 2 symbols are differing only by 1 bit, this is the so called gray coding approach. Okay. When you transmit phase 0, you are actually encoding that phase 0 by 2 bits. In other words, if you want to transmit 2 bit sequence 0 0, you transmit a signal which is say cos omega st, where omega s is the signal frequency, plus 0 degrees. Okay. If you want to transmit 0 1, right, so you group 0 and 1 into 1 bit sequence, then you transmit cos omega st, but this time shift the phase by 90 degrees. Similarly, you can fill up for the remaining 2. So, what has happened now is the bit rate, okay, or the number of bits per symbol has simply gone up by a factor of 2, and the spectral efficiency doubles up compared to the on off keying system. So, any 4 state spectral efficiency would then simply double up the spectral efficiency. If you go to 8 array PSK, okay, so if you go to 8 array PSK, the corresponding phase states that you have will be, so you have a one phase state here, then you have a 45 degree, then you have 90, 135 here, you know, and these are the 8 possible states. Okay. So, these 8 possible states can then represent groups of 3 bits. So, you have 0 0 0, 0 0 1, 0 1 0, 0 1 1, 1 0 0, 1 0 1, 1 1 0, 1 1 1. In this case, I have not used gray coding, but I have used what is called a straight binary coding. Okay. So, your spectral efficiency triples. In practice, it would not be exactly triple because of the imperfections involved. So, it would be slightly less than 3, but theoretically at least you are using the same bandwidth, but you are transmitting more than or equal to 3 bits per symbol. Therefore, your spectral efficiency shoots up. Okay. You can then go to even exotic constellation called as 16 QAM. This time you have many implementation choices. So, you can for example pick one of these. Here you take one inner ring of 8 array PSK, okay, and then on the outer ring, which corresponds to an increased transmit power, you pick one more 8 array PSK. Okay. So, if you now look at the total 16 combinations and then assign the binary counts, you can try this, you know, 0 0 0 0, this would be 0 0 0 1, okay, you have 0 0 1 and then you have 0, the corresponding bit here is 0 0 1 1, okay. This way you can actually fill up, and we will see how to implement a modulator in order to employ this one. So, this is called as 16 QAM in the star configuration, because you have 2 circles over here, okay. It is also possible to have a different kind of a QAM. This is called as the square QAM, okay, and in the square QAM, as you can clearly see, they are arranged, the symbols are arranged in the form of a square, okay. So, this is one way of increasing the spectral efficiency. This is 16 square QAM. You can also go to 64 QAM, but I am not going to talk about that 64 QAM in this particular module, okay. So, you have all these options in which you are able to transmit more bits per symbol, but what exactly is the catch here and what is the other approach? In order to answer these questions, just wait for the next module. Thank you very much.